indeterminate form. Then we're going to start learning about the L'Hopital's rule. So a lot of times when you're taking the limits, let's say a lot of times you're taking the limits of a function, and limit point going into a specific value, or it can be this, limits at infinity. So anytime you're taking these kind of limits, you may run into the kind of problem where you may run into the limit like this, infinity over infinity. Or you may run into 0 over 0 anytime that you're taking the limits. Okay. And it's not like completely brand new for us. We've seen problems like this before. Let's say you take the limits, right? X is going to 2 here, and that's x squared minus 4 over x minus 2. Something like that, right? I mean, if you follow the basic limit law, you go immediately into a 0 over 0. Well, there you go. That's and then you go with something like this. Limits to infinite, x squared minus 5, right, and over x squared plus 4x plus 3, something like that, right? Right hand behavior of these two. That one here, leading coefficient is 1, right, and degree is 2. Leading coefficient even, the leading coefficient is positive, degree is even, so it's going positive infinity over positive infinity. Right? We've seen these all over. And so these right here, these kind of limits, okay, we refer to them as a famous name right here. This is called the indeterminate form. Indeterminate forms, right? And so that brings us into the first form here. Anytime that you have a infinity over infinity or 0 over 0. See, it's indeterminate because the answer cannot be obtained directly. The answer must be done something else. See what I'm saying? Now, people mistakenly think about infinity over infinity as you cancel out the infinity, making it 1. So they say, hey, there's an answer. But that's not correct. You see what I'm saying? Now, we can't cancel infinite. And then 0 divided by 0. Okay? You can't cancel the 0 to make 1. Nope, it doesn't work that way. See what I'm saying? Now, so it's indeterminate in the sense that it may turn out into a lot of other values like that. Okay? And so, and you have already seen, we've had throughout our times learning limits problem here, limits of like an e to the x minus 1 over x. This famous limit that we've learned way back right here, right? It really, if you follow the limit laws right here, it's just going to give you a 0 over 0. See what I'm saying, no? Right? But 0 over 0 over here, we don't cancel the 0 to make it 1. We did other way. We used other methods to come up with it coming out being a 1 like that, right? But not because we cancel out the zeros. See what I'm saying, no? Because otherwise, see the limits for a to be x minus 1 over x right here. That limits, yes, indeterminate again. But if we think about just brutally canceling out the zeros, it's going to be 1 enough. It's not going to equal 1 because it's not the real answer we've learned is natural log of a. Right? So there's now we're going to learn some good way, some good solid way to handle these two indeterminate forms right now. See what I'm saying, no? Okay. And so with those two indeterminate forms, you have what's so-called a L'Hopital's rule to handle. And it's not like we don't know how to do indeterminate form before. Some of the problems with the indeterminate form, we already had a way to handle the problem. But here I'm talking about in case where we don't have any of those tools anymore, then we can still have a tool that being the lifesaver here. So that's called the L'Hopital's rule. P of x, Q of x, continuous function. 0 over 0 or infinity over infinity. Starting out with some function and we're setting it up as a ratio because being a ratio is the way to get it there for being indeterminate. That form 0 over 0 or infinity over infinity, right? So in that case, here's what the L'Hopital's rule says. As long as you can show to point out it's indeterminate, right? Limits Q of x over Q of x. Not necessarily a rational function. It's equal, proven be equal to the limits of some two new function, p prime of x over q prime of x. So s get to a. A can be an infinite limit. So let me do a quick demonstration of what this is all about. Just think about it this way. So we had a function. Right? We have, let's say we take the limit as x going to infinity. And I should have mentioned as well, this is also applicable to limit at infinity as well. Right? Because right here I use generally limits coming to a limit point here, right? But it also applies limits to infinity. Right? But let's say we have a problem like this, 3x minus 1, right? And over 4x plus 1 here. Now, right out from the limit laws, this gives me positive infinity over positive infinity. You guys agree? But the way how I'm seeing it, and it's not like we didn't know how to handle something like this. Of course, something like this, from back then, we already learned that we can do limits, right? X to infinity of this 3x and minus 1, I multiply with the denominator 1 over x, right? And 4x plus 1 right here, I multiply with the denominator. The denominator is degree right there, 1 over x, right? And I multiply it in, and we get really it's a 3 minus a 1 over x, right? And over a 4 plus a 1 over x. Okay? We take the limits here. Right? This limits, and it came down to a 3 minus 0 over 4 plus 0, making it all 3/4. You guys following? We are, so that's just a reminder of the method we used back then. Okay? But then on top of that method, because that method is limited to only limits at infinity, and we got rational functions. See what I'm saying? No? But that's just to point out again for you guys that we already seen this kind of indeterminate form existing before in our the work, the time with limits. But so here's the thing: the L'Hopital's rule that we just now learned introduce a new method on top of that, right? Introduce a new method that we can arrive at the same answer we before as well. So here's how we're doing it. You see, I'm seeing this as some function p of x. You know what I'm saying? No? And then that bottom denominator here is another function q of x. Right. So now the limits at infinity of this 3x minus 1 right here over 4x plus 1. That is the same according to L'Hopital's rule. That is the same as take the derivative on the numerator being a 3. The derivative in the denominator being a 4. See what I'm saying? No? Right. Take the prime of that. So, or for short, just do the prime thing, right? 4x plus 1, do the prime thing. Two separate derivatives stacking on top of each other. And we take the limits, right? Again, it will turn out equal. Right? It turns out the same limit. And so in that way, what I see here is the derivative of 3x is a 3, right? Derivative of 4x plus 1 is a 4. And that limits here, okay, come out as easy as just 3/4. See what I mean? So that's the idea right there. So L'Hopital's rule says sometimes when you take the limit on a ratio at the limit point here, and then that ratio unfortunately gives you an indeterminate form, either a 0 over 0 or infinity over infinity. You can just simply bypass doing that, but instead you're doing the limits, the same limits, but on the two other functions, p prime over q prime. Right? That's the idea. All right. So now let's look at some actual example here. Let's call that example 1. So let's evaluate the limits, right? About 3 to the x minus 8 to the x over x. Here. Part A of our problem. It's the limit as x is getting close to 0. Right. So but here's the way how we use L'Hopital's rule. You have to indicate that we run into an indeterminate form before you use L'Hopital's rule. See what I'm saying now? Because otherwise, if your limit laws comes out immediately into some limits, then please don't use L'Hopital's rule. Otherwise, you're going to give an incorrect answer. So first of all, I can see that this here, according to limit laws, x going to 0 and numerator 3 to the x minus 8 to the x, right? Over limits of x right here, right? These are all continuous functions. So it's just simply substituting in, so 3 to the 0 minus 8 to the 0 over 0. See what I'm saying? Huh? And it gives me 1 minus 1 over 0, which is a 0 over 0 indeterminate. Right, so you got to show that using the limit laws, the basic limit laws, we run into an indeterminate. And it's even better that we make a note here. indeterminate. Okay? Indeterminate. Okay? And so now something like that, now we can start doing this. Okay? Now when I start using the L'Hopital rule here, so that limits, right? 3x minus 8 over x. I'm going to roll back to that beginning point, that limit problem we desire beginning. According, this is just a style that I picked up from my favorite professor back then right here, but it's equal to the limit according to L'Hopital rule. So I put the little symbol, the LHOP right here, right? On top of that, indicating that yes, it will come out the same as the following limit work. But that's a guarantee by the L'Hopital rule. Right? So I've been forming into that the habit ever since, putting a L'Hopital symbol on top anytime I was about to use L'Hopital rule. Right? So it's a limit as x go to 0 again. But now I'm not going to do the limit on these two functions anymore. I mean, of that overall function with those numerator and denominators. I'm taking the derivatives. Right? So the derivative in the numerator here is you guys do remember, it's an exponential with base other than e right there. So it's 3 to the x times the natural log of 3. Right? For the first term, minus now 8 to the x times natural log of h. Right? For the second term, and the derivative in the denominator here is simply just 1. Right? So that now gives me, now let's see if we can go with the basic limit laws from this step right here. So that connection here is according to L'Hopital's rule. And once we arrive here, and now it's a lot easier, right? It's just now 3 to the 0 times the natural log of 3 minus 8 to the 0 times the natural log of 8, right? Because the numerator is 1, of course, it's free from 0, and it's continuous. This other function right here, they're all continuous. So we can substitute it in, and now that's making it just natural log of 3 minus natural log of 8. You know what I'm saying, huh? Or you can write it as, for short, the natural log of 3h. We can use the L'Hopital's rule to prove a couple of results that we've done back then. So let's look at this problem here. Does it look familiar? Sin of x over x. So check the limits. It's x going to 0. Does that look familiar? So here's my intention. I don't want to treat this as a special limit where you guys just simply memorize the answer anymore. Do you still remember what that answer is? See? But I don't need you to memorize that up to this point anymore, okay? Because here's the thing. Whatever that I said about being a special limit, right? And try to make you guys remember throughout the quarter, but here's the thing. According to limit laws, right? Sin of x is a continuous function. You guys agree? Okay, so when x gets close to 0, it gives me a sine of 0. You guys following? Okay. And when x gets close to 0 in the denominator, it gives me a 0. So this clearly is, and what sine of 0, by the way? Sine of 0 is a 0, so it's indeterminate form. You guys following? Okay, so clearly this guy here is indeterminate. Indeterminate. Let me just write it for short. ing for indeterminate. Okay. And so now we're going to use, I'm not saying that this was the proof for this special limits, but we can now use the L'Hopital's rule to use this problem here as an example to show how the L'Hopital's rule can apply to. So this limits right here. Once we know that we run into the indeterminate form, we can do that according to L'Hopital's rules, right? We can just simply take the limit of sine, which is giving it cosine of x, right? That's the limit. That's the derivative of sine on top. Over what's the derivative in the denominator? 1. So cosine of x over 1. You guys following? Right? And then we still stacking those two derivatives. We're still stacking those two derivatives on top of each other, right? Like how it was in the beginning fraction. But now we take the limits again as x going to 0, same limit point. See what I'm saying now? Right? What does it give me now? Cosine is still a continuous function. 1 now is completely free from 0, right? So we got a what? Cosine of 0 over 1 over here, right? Which is 1. You guys clear on that so far? So we can use the L'Hopital's rule now to clarify, right? To make clear the result. We've been keeping that as a special limit. Yes, we use table of values to come up with the limit 1 for that, and we've been treating that as something to remember. You know what I'm saying? But now you have a way to calculate it formally. See what I'm saying? Huh? Okay? And so now before I go too far into the L'Hopital's rule here that we've learned, I have to make sure you guys understand. Please, it's not the quotient rule when we were taking derivatives, okay? Here we're talking about we're taking two separate derivatives and put them on a fraction in the same order of how they started with those two functions. See what I'm saying now? Okay? Over my years of teaching, I keep having students. Eventually, somebody is going to mistake that as a quotient rule. Okay, but it's not the quotient rule. Okay. All right. So let's look at the next one here. And again, L'Hopital's rule applies for a good mix of limit problems, including those limits at infinity. So how about let's look at part B of the example here. So now looking at limits of 11x squared over e to the 4x, right? And let's take the limits here as x going to positive infinity. Okay, so for this problem, once again, here's how I'm seeing it. If we are applying the direct limit laws, right? The direct basic limit law here, I'm gonna have the limits for 11x squared, right, over limits, right, for the e to the 4x. Okay, as x is getting close to positive infinity, x is tending out to positive infinity. And that's clearly giving me infinity over infinity. See that? Huh? Right? And once again, keep in mind, infinity will never cancel with the other infinities. Right? So we can't just cross it out and making it 1. Right? So it's not going to work that way. So here's how I'm seeing it. So that brings about that we're looking at an indeterminate form. Right now it's indeterminate. So now, once we pointed out that it's indeterminate, then we can start using the L'Hopital's rule. X approaching infinity for 1 over x, 11x squared over e to the 4x, that can be equal to the limit according to the L'Hopital's rule. Right? That can be equal to the limit of this function right here. The function created by taking the derivative on top, making it 22x, and taking the derivative in the denominator, e to the 4x times 4. You guys agree with that still? But what's wrong with this step right here? We've done the L'Hopital's rule once, right? And from this point on, can we carry on with the limit laws? It's still going to give me infinite over infinite, right? And infinity over infinity. Am I correct? Because the 22x is going to rise to positive infinity, right? And then this 4 times e to the 4x is still going to rise to positive infinity. It's indeterminate again. So what do you suggest? Yes, we do the L'Hopital's rule again. We apply it again. Right? So from that point, it's going to again equal according to L'Hopital's rule. Right? I'm going to take the derivative on these two separate functions. See what I'm saying now? Because what's failing for us right now is that this function here, 22x over 4e to the 4x, runs into an indeterminate. So taking that derivative, taking that limits is the same as according to L'Hopital's rule. Taking the limits, right? Same limits, x approaching positive infinity. Right? But now I'm looking at 22 over, now it's 16 e to the 4x, being the derivative of that 4 e to the 4x. So now this example problem here points out for us that we can indeed, right, take the L'Hopital's rule as many times as we want. And that should have been labeled as part C as our problem. Okay. But so now, have we arrived at some answer that we can take that? You see, the 22 on top is the constants, right? Whereas this denominator keeps growing. You know what I'm saying now? So the overall answer now comes out 0. You know what I'm saying now? Denominator stays constant. Numerator stays constant. Denominator keep growing. That's where it goes to 0. It's legally approved. Yeah, right? Okay. So as far as the indeterminate forms here, back on what I introduced earlier, right? So we have the L'Hopital's rule that can handle these two indeterminate forms, right? So L'Hopital's rule applies for these two cases here. Applies to these two indeterminate forms. Okay. Now the sad news is that there are other indeterminate forms out there that L'Hopital's rules do not apply immediately. Okay. So now let me point out for you guys. We can have something like this, an infinite minus an infinity. That's another indeterminate form right here. And be aware that L'Hopital's rule does not apply directly to that. So don't create the two derivatives and subtract them out and take the L'Hopital's rule. It's not going to work that way. Okay? So L'Hopital's rule only applies to these two indeterminate forms. But there are some other indeterminate forms that L'Hopital's rule does not apply. Okay, and then we have 1 to infinity. We have a 0 to the 0 power. We can also have infinity raised to 0. We can also have 0 times infinity. These are some other indeterminate forms there. I have to emphasize one thing. The other guys, make sure you be aware that L'Hopital's rule does not apply directly. Or in other words, there's no L'Hopital's rule applied for those cases, for those indeterminate forms. So let's learn one by one how we can handle some of these. Example 2, let's evaluate the limit again. Part A, how about limits? X times natural log of x. We're letting x get close to 0 from the right-hand side. Yeah, so you're talking something like this, right?
Yeah.
That's considered the same as that.
Okay.
So it's just a sign right here. So we just mainly, you can isolate out the sign right here and consider this, whatever that limit will turn out using the L'Hopital's rule. And then we put the minus sign back in. See what I'm saying now? Right? And so that, we don't have to worry about that. But there's these other forms right here that L'Hopital's rule doesn't even apply directly with them. We're starting to learn that here. So now let's get back to that example problem that we have. Limit law says as x gets close to 0 from the right-hand side on the x right here, right? We can multiply the two separate things right here. Limits of x gets close to 0 from the right-hand side on the natural log of x, right? We can multiply these two, and that's making it what? A 0 from that factor, right? But multiply with negative infinity from the natural log function. You guys follow me on that so far? Because here's the problem. The natural log function looks like this. Right? Asymptotic as vertical asymptote here is x equals 0, right? And as we get close to 0, see from the right-hand side of the function, the graph keeps going closer and closer and closer, but it drops down negative and drops down negative. See that asymptotic end of our graphic there? Right? So that's why we're looking at this case here. Right? That's the indeterminate that's, remember, right now at this moment, L'Hopital's rule does not apply. Right? So here's what we handle. So we can handle that into something like this. I'm going to purposely rewrite, right? This limits problem x times the natural log of x. X is getting close to 0. I'm going to rewrite it as, you've got two choices. You can write it as a natural log of x over 1 over x. You guys agree with that algebraically? X times the natural log of x is the same as natural log of x divided by 1 over x. 1 over x. Okay? And we'll take the limit as x gets close to 0 on the right-hand side. And indeed, this is to your answer right here. You were asking about what if we have a sign without infinity, right? This guy here gives me negative infinity. But that guy gives me positive infinity. Because the graph of the 1 over x is growing up to positive infinity as we get close to 0, right? From the right-hand side, the graph grows up again. You know what I'm saying? But we still consider this under that big indeterminate form that the L'Hopital's rule applies here. Am I making sense? So, what did we learn here throughout this problem? Yes, it started out being some indeterminate form that L'Hopital's rule didn't apply yet. But we can algebraically rearrange our function so that we can make the indeterminate form where L'Hopital's rule applies. See what I'm saying? Right. So now I'm going to stick with treating the function as something like this. So now with the indeterminates here, right? Yes, it's now real good indeterminates. Right. But here's what I can do. Now I'm going to check the derivative, top and bottom. That gives me a 1 over x, the derivative of log natural log, right? What's the, you guys, papers and pencil, check the derivative of 1 over x for me. Right? Negative, yeah, x to the minus 2 power, so you can write it as negative 1 over x squared. You guys agree? Right. Yes, or negative x to the negative 2, I agree. Letting x go to 0. So it went from here to here based on the L'Hopital rule. Right. But so this one here is indeed no longer indeterminate, because here's why. It cancels out, right? 1 over x divided by negative 1 over x squared, it turns into, it's the same as the limits of the minus x, right? We're letting x get close to 0 from the right-hand side. You guys get that still? So 1 over x, right? Over a negative 1 over x squared algebraically equals to negative 1 over x times with x squared over 1, right? X squared cancel with x, making it minus x. That's why I got that. Right? So that's some algebra. So that gives me simply just a 0, right? Yes, because the function minus x goes like this. So now as you're getting close to 0 from the right-hand side of that, right? It goes coming back to 0 for y value. Okay? And then you know what? Let me change my I changed my mind a little bit. Let's call this the only problem in example 2 here. But example 2 shows how we can handle the case where we have a 0 multiplied with an indeterminate form, right? 0 multiplied with infinity. Okay? A lot of time we turn that into, as a conclusion out of this problem here, when you have the limits, right? X getting close to a of a product of x times g of x, and it runs into a 0 times infinite. Right? When we run into that indeterminate form, the common generality here to handle the problem, we can make it g, okay, over 1 over f of x. That's one way. See what I'm saying now? Or we can make that as f over 1 over g of x, because thus any one of these will give us a 0 over 0 or infinity over infinity. So that's 2a. Right? We can rewrite our function, our beginning limit, into one of these two forms here. So L'Hopital's rule we apply here. Right? That's the general the way that we've been handling it. That's one good generality of that. I'm going to take you guys into example 3, where I introduce another class of indeterminate form here. Among those that I listed, so I'll have a part A here this time. Let's say we want to take the limits of x getting close to positive infinity. Right. You see this one right here. Again, what's wrong with that? Now, this term we grow to, the 2x goes to infinity times 1 right here, because as x gets large, right, 1 over x goes to 0. So e to the 0 is 1. But minus another infinite right here, the 2x. You guys know that too? Okay. So it's technically infinity minus infinity. Right here is indeterminate. Indeterminate. That's what I'm trying to point out for everyone. Okay. And this one among those other forms of the indeterminate, that L'Hopital's rule does not apply immediately. Okay. So in this case, how do we handle a problem like this? So once again, it's when it gets to infinity minus infinity, it takes different variations. It takes different ways to approach it. But for a problem like this, I can do something like this. The limits x to positive infinity of the 2x times e to the 1 over x minus 2x. You guys can observe that we have a common factor here, right? We can purposely factor it out, making it 2x times the e to the 1 over x minus 1, and then taking the limits to infinity. And this form right here, by doing this, we run immediately into, that gives me, see, this 2x runs into an infinity, right? That's here is 1 minus 1 gives me a 0. Right? It's still another indeterminate. But now we can do the following. So realizing that indeterminate, we can do this. Yes, I can treat that algebraically. I can apply some treatment. E to the 1 over x minus 1 over 1 over 2x. You guys follow it? Or actually, it's smarter that I can go just 1 over x right here and keep the 2 on top. It doesn't change the problem too much. Because really, the x is what causes growing to positive infinity, right? The 2 is just a coefficient. So in this way, now, yes, it will go to 0 over 0. In this final indeterminate, I can apply L'Hopital's rule. So now, according to L'Hopital's rule, right, I'm going to take the derivative of top and bottom. So that gives me 2 e to the 1 over x, right, times 1 over negative 1 over x squared, right? And then minus 1 becomes 0. And then the denominator here, I have minus 1 over x squared again. Here I take the limits of x going to infinity. See how I was doing that? Yeah? So I took two separate derivatives. So that now cancels out. It will cancel out the minus 1 over x squared, making it now 2 times e to the 1 over x. Right? And we're taking the limits as x goes to infinity. Right? So now we don't need L'Hopital's rule any longer. That comes out just simply equals what? 2 times e to the 0, right? Which makes it 2. See how that problem works again? And so with this one here, it's easy to see that the limits would run immediately into, according to limit laws, right? We can do that term by term, right? And the first term here gives me an infinite value, and then the second one here also gives me an infinite. Right? So we fall right into that infinity minus infinity indeterminate form again. And so once again, this rings a bell that we can't directly use the L'Hopital's rule. But so here's the thing. And when it comes to this family of indeterminates, the infinity minus infinity right here, there's not a hard rule about how we solve it, so it does take some creativity to work on the algebra. And it's impossible for me to cover every example out there, so when you guys work on your assignments problems right there and face something like this, right, and face some difficulty, you let me know. With this one right here, we can factor out the x, making it now x and e parentheses as a product between x and multiply with 1 minus a natural log of x over x. You guys repeat that? Okay? Then take the limits, right? It's x going to infinity. And so the limit laws has been allowing us to do, yes, we take one separate limit on the x, right? Which is easy to find. See what I'm saying now? And then multiply with the one separate limits on this one right here. 1 minus natural log of x over x. You guys are doing that still? Okay. And then so allow me to take a quick branch out right here. I'm going to separately, okay? I'm going to hold on to this work and I'm going to come back and finish it out. But I'm going to hold on to this work and I'm going to do something like this. Now, just think as of the separate limits of the natural log of x over x. Okay. That's separate limit right there. Natural log of x over x, right? And we're letting x going to infinity. Now this limit here on its own will come out infinity over infinity. That's where the L'Hopital's rule can handle. See what I'm saying now? Goes right into that that indeterminate form. That L'Hopital's rule is applicable to that, right? And so now with this one here specifically, right, it's indeterminate. Right? And so now I'm going to use the L'Hopital's rule just to find the limit on that particular term right here. So that's leaving its limits. According to L'Hopital's rule, we can find the limits. Same limits, but slightly different function. We take the two separate derivatives. Derivatives of natural log of x gives me a 1 over x, right? The derivative of x here gives me a 1, right? According to L'Hopital's rule. So that means this limit here will come out being precisely what? 1 over x, right? X to infinity and over a limit of 1 right here, right? That's x getting to infinity. So that's just going to be a 0 over 1, right? Which is completely okay. Right? A 0 over 1, which is a 0. Right? And so now with that result here, now I'm going to come back and wrapping this up, maybe finish this up. So this limit here, yes, it gives me limits x, right? It's x going to infinity. That limits here, limit laws, once again saying that they can take two separate limits, right? So multiply with the parentheses and the limit of the first term, 1 minus the limits, right? Of the natural log of x over x. We are taking limits as x going to infinity. But now what does this give us here? The limit, the limit of x right here, infinity. You guys agree? Okay. We multiply what's now this one right here, first term is a 1, right? And the second term is a 0. And that term came out from that separate result that we have done it. So now that's making it now just simply infinity times 1, which is completely okay. This is not among the indeterminate form. So that comes out just simply being infinity below. So, you know, because infinity minus infinity itself can sometimes be quite dangerous. Right? It could be an infinity, or I mean, the answer could be some finite value, or the answer could be some infinite like that. So it's best that we do some algebra, or we do some work around that, right, to turn that into some form that we can recognize. But then, how exactly we're going to do that? It takes some creativity, and it takes some time working around with a different solution in different directions. Okay. All right. We're still evaluating limits. With this example here, let's evaluate. Okay. So, I'm a part A. We want to find the limits of as x gets to positive infinity of the function x to 1 over x power everything. So this one right here, when we apply the limit logic, this is what it gives me. It's the same as taking the limits of x, right, and raise the power of limits of 1 over x as x to infinity. You guys seeing that the limit laws is leading us into something like that, which will lead it into this limit of x as x to infinity. It's infinite, right? But 1 over x as x approaching infinity is going to give me a 0. So that falls right into those indeterminate forms again, right? One of those indeterminate forms of infinity raised to the 0 power, where the L'Hopital's rule does not apply directly on this. So in that way, right here, here's how we can actually handle this. So now I know it's indeterminate. So I'm going to say, let's say the limits here. I'm not talking about the L'Hopital's rule yet. I'm just going to say the limits, the overall limits from the beginning. Let's say it's going to equal some value. It may be finite. It may be some non-existent value. It may be some infinite. But let's say it's going to be something, right? The limit there is going to be something. So here's my work. Think about, I'm going to take the natural log of both sides, right? I'm taking the natural log of both sides. The limits of x, the 1 over x, right? X to infinity. That equals the natural log of L. But that limit can be just whatever, but we take the natural log of L, the natural log on both sides. So the right-hand side is pretty much done because it's natural log of some number right there that we're holding it, that we still finding out. But then the left-hand side, there's some work that we can do. Now remember, the natural log function itself, right, is a continuous function. So taking the natural log of the limits is going to be the same as taking the limits, right, of the natural log of that function inside, all due to continuity like that. So remember the continuity, that we can just swap the limits from the inside out like that. And so now let's continue the steps. Now the natural log that we've seen right here, right, on the left-hand side, limits x to infinity, but the natural log of x to the 1 over x. Now we can rewrite this algebraically as 1 over x, multiply it down and multiply with natural log of x. Right? And that equals natural log of L. Or another form of that is going to be limits, right, of natural log of x over x. Right? As x is getting close to infinity equals natural log of L. And so in this case, I am going to extract out and work specifically, separately on that little step like that. So, as a star work right here, right? This is what I'm going to do. Just one separate limit of natural log of x over x right here, right? X getting to infinity. Now this one right here does go into a 0 over 0. I mean, infinity over infinity. Okay? And so that is clearly an indeterminate that L'Hopital's rule can handle. Indeterminate. So now, according to L'Hopital's rule, this limits here, right? According to the L'Hopital's rule, right? That can be 1 over x, right? Over 1. We take the limit as x is going to infinity. right? And that gives me a limit to 0, right? And it's very similar to that component of the work we've done in the earlier example. So now what does that mean about this? That means this limit's here back on this work that we're halfway, I mean, we're almost getting there. It's 0, right, equals natural log of L. The limit we found specifically for that natural log of x over x came out equal 0. We have just proven it here on this separate space here, right? So that means back to this equation that we're going through, the natural log of L, the way it reads now, natural log of L equals 0. So what does that mean right here? Remember, L is our limits from the beginning that we don't know the value yet, but we're tending there, right? We're trying to get there. So now that means what? From here, L equals what? So what base is this? Logarithm, base e, right? E to the 0, or it's indeed just L equals 1. So we found that limits here being 1. Right? So we've learned, actually, right from this example problem right here, we've learned a little bit of some good experience. So the situation, like those indeterminates where it's a 1 to infinity or infinity to the 0 power, right? Or even the 0 to the 0 power, these forms are here. A lot of times, commonly they come from the kind of function where we have some f of x and being raised to another f of g of x power. So it's not really an exponential function. An exponential function requires a fixed base, a constant base, and raised to some expression. But here it's some function, f of x, and raised to another function, right? And then we take that limit, like that. See what I'm saying now? Right? To a, whatever the limit turns out. So these limits, these indeterminate form, like I said, a lot of time likely they came out from this general setup for you. So the way we can commonly do, and I'm not saying that it guarantees it works all 100% of the time. I'm not saying that, but it works. The method I just introduced for you guys, it works for about the higher than 90% of the time. Okay? But we are starting out thinking of that as equals some limits that we did, some unknown limits. Right? We have some unknown limits, and then we take the natural log on both sides. Right? The natural log of the limits f of x, right? Raised to the power of g of x. You know what I mean? Right? And that equals natural log of L. And then from there, yes, we can swap the order of the limits. Operation can come out. Turn out we can take the limits, and then here's the natural log of that f of x being raised to the g of x power, and then equals natural log of L. And that means that we can break it down as the same limits for here. It's g of x. Right? That power multiplied down, right? Multiply with natural log of the f of x. You guys read that? Right? And then we can start learning or start taking the limit of this separately. Right? But that does take some creativity as well. Again, so come up with some general guideline. It's only a guideline. It's not a hard rule, but that guarantees it will always work. But let's say with that rule right there, with that quick little suggestion, we can apply that and solve another limit problem here. Okay. The work may get a little lengthy, but it's okay. Let's say we want to find the limits, right, as x is approaching positive infinity of about 1 plus some constant a over x, right, raised to the power bx. Okay. Make a note on that. A, b, right, or coefficient, or some constant values. So only the variable x is the one that's changing. So let's see how we can work on that. So with this limits right from the beginning, right, the limit laws are now saying that, well, we're going to quickly go into this. We're looking right into this. You can see that this limit right here, we go to what? 0, right? That's the whole a over x right here. A stays constants, but as x gets large, right? The x gets large, the whole thing here will go to 0. You guys following? Okay, so that gives me a 1. 1 plus 0 gives me a 1 raised to the power infinite right here, right? And so in that case, we're looking right into that indeterminate form 1 to infinity. Indeterminate. Okay, that's the issue again. And so now I'm going to apply that strategy that we've had. And yes, it does stay in the form of a sum f of x, see, 1 plus a over x, right? Sum f of x raised to another power being the g of x, right? So we can do that. So I can do this. Let's say 1 plus a over x all raised to the power bx. That limits, right? Let's say it's going to equal to some unknown value L. It's going to equal to some unknown value L. And then I'm going to do this. I can see that I can, yes, take the natural log both sides, right? The limits work. X is going to infinity, right? 1 plus a over x to the power bx. Right? I'll take the natural log of that, and that means it's the same as taking the natural log of L. So in this way right here, I can see that my right-hand side, there's nothing much we can do, right? So let's leave it the same right here. But let's look at the left-hand side. Again, I can swap the order of natural log with that limit operation right there. So that now means I can take the natural log of, see, there's 1 plus a over x, right, all to the bx power, right? And then we take the limits, right? As x is going to infinity, right? Natural log of L. And that further now means this left-hand side here becomes, it leads down to, we're taking the, yes, it's limits, right? But bx multiplied with natural log of 1 plus a over x. And all of that there is all expected to equal natural log of L. So now let me branch out a little bit. So that work on the left-hand side, right? bx times the natural log of 1 plus a over x here. As you take the limits, as x going to infinity, that gives me a 0. I mean, that gives me an infinity, right? And that's here give me, what do you guys think? See, that goes to 0, so natural log of 1 is, I mean, that goes to 0, but 0 plus 1 is a 1, right? Natural log of 1 is a 0. It goes into infinite, infinity times 0 right there, indeterminate. Okay, so this is what we can do. This is similar to some of the earlier examples we've done where we have 0 times infinity, so we can make one of the two functions in this product, right? We can make one of the two functions to be in the denominator as a reciprocal. So I can make that the natural log of 1 plus a over x over 1 over bx. And that's now clearly making it fall into 0 over 0 limits there. It's an indeterminate, but L'Hopital's rule I can handle. Right? This one here is another indeterminate, right? But the L'Hopital's rule now can handle this one just fine. Here equals this, and now according to L'Hopital's rule, this is what I can do. I can take the derivative both top and bottom, so it gives me 1 over 1 plus a over x, right? And I'm multiplying with the derivative of the inside. The derivative of the inside here giving it just minus a over x squared. And then the denominator here gives me 1 over b, right, times a 1 over x squared as well. Limits. X is going to infinity. You now see that I can algebraically rewrite this as, in this word right here, this in parentheses, I can rewrite this. And it's just optional to explain it. It doesn't have to be written down. But I can see that as an a. This one right here is an a times a negative 1 over x squared. How's that? It's easier that way. And this one here is already a negative 1 over x squared. So yes, we can cancel, my point is we can cancel away these right here. See what I'm saying? No? Okay. We cancel away that's leaving it a top. Okay, so now that limits here algebraically reduced down to limits. Okay, x going to infinite. And we got 1 over 1 plus a over x, right? Times a here, divided all of that by 1 over e. Okay. Okay. That's now making it really, let's clean up the term here. Yes, it's limits. Now I have really just ab, right, times 1 over 1 plus a over x. Take the limits as x goes to infinity. And then now as x gets large, right, that is the this is a one bigger group of coefficient, right? That's just one big coefficient. The only quantity that's changing, depending on the limit right here, is the a over x right here. That goes to 0. So 1 over the 1 plus 0, making it what? R just 1 here, right? So the final limit here comes out here in A. So AB, that left-hand side of that. So now that means we can bring it back. Right? We can bring it back to this work. So the entire left-hand side here is derived to be just the limit AB. The limit AB equals natural log of L. So our real limits that we were looking for is that limit L right here. We're still currently unknown, but we have a relationship. Natural log of L must equal AB. And so from here, what can I say about L right here? That means I can say that L is base E raised to the power AB. You guys good? All right. And so in that way, now consequently, that's our limit. Right? That's our final limit. E raised to the power AB. Right? Looking a little strange. But this problem I brought up right here has a good significant impact in a lot of your work later on. Think about this problem right here. Most fundamentally, there's this function right here. 1 plus 1 over x raised to the power x. You will see this once in a while. Right? I'm talking about some good application of the problem we've just done here. You see it's a being 1, right, over x. So 1 plus a over 1 times bx, 1 times x. Okay. So the answer to this, according to the work we have just derived, e to the a times b. A is 1, b is 1, so it's just e to the first power, just e. So yes, the limit like that, right? It's going to come out just simply e. All right. And so that covers all of the limits problem that we can use with the indeterminate form like that, and see how the L'Hopital's rule can apply.